This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
Hey, hello, and welcome to another episode of Design Safe Radio. I'm your host, Dan Zahner, and with me today we've got Dr. Ben Schafer, who is the William and Lillian Hackerman Professor of Civil and Systems Engineering at Johns Hopkins University. Ben, it's good to see you.
Yeah, it's great to be here.
Give us just a 60-second intro about yourself and a little bit about your research before we dive into the deep end.
Yeah, sure. So Ben Schafer, I've been a professor at Johns Hopkins for 24 years. I worked in practice at Simpson Gummerson Hager for a little while and still have a consulting relationship with them. And, you know, back long before that, Cornell and all those good times at the University of Iowa as a student. But I've been working hard as a structural engineer, primarily in steel structures for my career.
Excellent. So a lot of us, people in our audience, they might be familiar with how concrete buildings are constructed or wood frame structures and how those can be seismically resilient, but not so much with steel, like the red iron steel that we see, riveted together, welded together, or cold form steel or CFS, which is what your research focuses on. So can you talk a little bit about, you've been at this for over a decade, but even back to before NHERI was a thing and back to the NICE days. What is cold form steel? Let's start with that. I'm a mechanical guy, so we got to start with the material.
Sure. Yeah, awesome.
Then we'll go into how it's used.
Yeah, so cold form steel, in comparison to hot rolled steel, is just a designation of the actual shape that the structural engineer specifies is cold bent into that shape. There's a number of processes for doing that. The more important thing to kind of understand is, like, you can make steel from sheet and coil. If you do, you're making cold form steel. You can make steel from plate and bar and shape, thicker things. That's generally going to be hot rolled steel. And so as a structural engineer, you sort of start out with, I don't know, you got like 2 millimeter thick steel, or 68 mil still, and depending on how you want to talk about it or whatever, it's pretty thin, right? And so what am I doing that as a structural engineer? So turns out you're doing a lot with it. Already today, large percentage of all the rack structures that are used in warehouses, all the secondary system for metal buildings. And then over the last 40 years or more, a growth in direct cold form steel framing. So started out pretty much mimicking timber, kind of stick style, replace a 2x4 with a 2x4 thin steel bent shape. Grew quite a bit in non-structural, just splitting up the walls. You'll see it in a lot of mid-rise and high-rise construction now, the non-load-bearing walls using light gauge metal, another word for cold form steel. But my primary interest has always been in when you want to use it for the structure. So you want to carry the load, stop the wind and the earthquake, provide a safe and resilient structure. But pretty much you're going to use sheet steel and, probably not more than 2 millimeters.
Yeah. Well, and some of the key differences of that is, as you talked about, is the wall thickness of whatever the final shape is. But also you go down to the microstructure of the steel itself is different than a hot rolled product and makes it lighter, but has some different advantages and disadvantages to it. Can we talk about
absolutely.
that a little bit?
Building
material.
Yeah, right. And to kind of put a modern spin on it, so you can kind of, people can sort of understand, like, most people are sort of aware of the fact that their cars are just built from sheet steel these days. So it's just spot welded and often glued together, little pieces of sheet steel to form the body of your car. We don't pay probably as much attention to it. We don't think about it, how much material advancement has gone into different steels that are used in different parts of your car. So the same way structural engineers, we want certain things to happen in our building in an earthquake. Mechanical engineers want certain things to happen in a car. And so there's a lot more variety in what you can get out of the ductility and strength out of sheet steels than you can get out of plate and shape.
Yeah.
So you can get materials that yield 3-4 times higher than what we typically use in hot rolled structural steel. You can get ductilities as large as you like, 40, 50%, or really
Wow.
small, depending on how you work the material. And so folks that work in sheet steel are kind of used to thinking more of the material as part of the design space. So it's not just steel, it's which specific sheet steel and what ductility and what strength do I want out of it. Like in a car, you might want right next to you in what they call the A-pillar, a lot of protection. So you might want a really strong cage or whatever, but up your bumper up front, like when my high school senior hit our Corolla against someone last week, I wanted it to dissipate a lot of energy. So it has
Yeah,
a sheet steel
exactly.
with high ductility. So, you pick and choose.
Yeah, and it's a lot different. Like it's funny you picked the car analogy. I actually used to work at a Subaru factory as a manufacturing engineer, and so saw a lot of sheet steel coming through.
Yeah,
But it's very different than like an old Land Rover and how, yeah,
that's
that's made
right.
from steel too, but it's plate, it's welded.
Exactly. So
That
that's that evolution in automotive is it parallels and leads kind of some of the evolution that you see that's been going on in cold form steel building construction for the last many years.
Yeah. And so this leads to now an advantage of the cold form steel in your research of how you can use those different ductilities, different elasticity, different strengths as ways to dissipate seismic energy and make
Right. So huge,
more
so you've got
stable.
this nice material design space. You can use different sheet steels, get different behavior. That's like the plus. The challenge, of course, is that you're choosing to use something really thin, right?
Yeah.
So the structural engineer has to own up to local buckling and other types of buckling limit states that occur inside that sheet steel and design, really incorporate them in their designs. And that's something that is very different, particularly when you start thinking about seismic and structural safety and resilience. So we tend to try to drive everything towards, particularly in the steel world, could I make it yield? Can I make everything go away except for this one thing that I want to have happen? Well, if you choose to build your whole structure out of 2 millimeter thick sheet steel, the local buckling is going to happen. So you have to decide, how do I deal with that kind of local buckling and also still get the energy dissipation that I want? So get it to happen in a certain location, in a certain way. So it's really, you have to up your engineering game a little bit to drive the behavior that you want.
Yeah, it sounds like if we got any electrical people listening in, it's almost making like a physical version of a fuse, so that you drive that buckling into a place that's easily replaceable, like a fuse, so that you can put that building back into service much quicker after an
Yeah,
event.
and that's been an important, kind of thought process for seismic structural engineers, and capacity-based design and those ideas, which really are really been important for seismic engineering and becoming more important for wind, as well as we deal with,
Yeah,
climate change and more challenging winds.
yeah, absolutely. So kind of walk us through what you've been working on since the Nice days and how that's kind of evolved over the years as we're getting into NHERI, and now we've got a really big cold form steel structure down
Yeah,
at
absolutely.
CFP.
I've been working on cold form steel since my PhD days, so 25 years
Yeah.
plus. And we're working basically in the early days on, could we make a better member for a person, right? So can we add a stiffener or choose the material a little bit differently? But the goal there was to maximize the strength, minimize the weight, pretty classic sort of objectives. And a lot of that work went into design specifications that engineers use. And that's kind of like phase one of my career, more or less, is, really focused on that. Um, since the Nice days, what we've been focused on is cold form steel being used in a system. What we found is our best calculations for the strength of like a relatively low-rise cold form steel building versus when we actually built one and tested it back in
Hmm.
the Nice tests at the University of Buffalo. The building was far stronger, far stiffer, and behaved much better than our sort of engineering calculation would have actually revealed to us.
Hmm.
And so that opened up this big puzzle of, okay, so this thing behaves really well. Why? Right? I mean,
Right. Yeah. Wait a minute.
what's it doing as a system that's different than what we expect as an engineer? And we start to really understand that the full building system, the cooperation between the structural and the non-structural, is a little different for cold form steel that uses repetitive framing than for reinforced concrete or structural steel that uses very widely spaced bays. And we sort of really only focus on the structural system. And so
Hmm.
working on that aspect has been a major part of the uncovering of how these systems really work for the last many years now.
Wow. Well, and on top of that too, it would glossed over another advantage of cold form steel is the sustainable nature of it as well.
Right. I mean, so yeah, cold form still has two kind of major aspects to it, right? I mean, you're trying to decrease the mass, use less material. I mean, it is a from its inception, it is a material efficiency idea, right? Can I use the absolute minimum material? And that's a big sustainability goal in general, because the embodied carbon of every piece of material that goes in, you can't get rid of it. The other aspect of sheet steel and coil steel, particularly in the United States, is that most of it is made from electric arc furnace recycled steel. So the recyclable content of steel, particularly domestic U.S. steel in sheet and coil, is very high. And so it's one of the few places where we actually have a domestic circular economy. That, I mean, that is totally real. I mean, so when you throw away your stove and it's got sheet steel in it, it does not just go away. I mean, it makes it to recyclable and, makes it onto a train and gets an electrode stuck into it and turned back into more steel.
We need
One of
to
our
find
small
some videos
successes.
of that to put in the show notes. That sounds
Yeah, well, we should talk to some of our friends at Nucor and places that do that on the regular.
yeah, absolutely. I mean, I could watch that for hours. But so you've been working on from now. I mean, this is a common way that from Nice and now NHERI, from seismic and wind and water, moving from calculation to test to discovery to subsystems and engineering type tests to back up to full scale systems. Um, what are some of those other research projects that you found since those days at Buffalo that are really interesting?
Well, there's been a lot. I gave you a little bit of the work that we did on high strength steel with cars. And so that was a large collaboration with NSF, with American Iron Steel Institute and other producers, to look at how could we take some of these sheet steels that have performance that are way beyond anything we're using in construction today,
Yeah,
turn them into structural members and figure out how to optimize them.
cool.
So that led to some changes in the standards that engineers can use, and a nice body of work around
Mm,
really improving the what advanced high strength sheet steels. So that was a lot of fun. That was experiments and modeling, and that's a common for me. Um, these days, we also, in collaboration with the American Institute of Steel Construction, with the Pankow Foundation, the Steel Tech Institute, and other friends, are looking at a bunch of lightweight floor systems.
oh
Some for like
wow.
commercial scale that are all steel, some that like shorter spans, commercial or residential, but 10, 12, 14-foot spans. And all non-proprietary. So it's just been a really nice collaboration with a bunch of people to look at, if I'm going to use steel because of its high recyclability content, but I need to get around some of these other challenges with low mass. Maybe I've got vibrations or acoustic concerns, whatever. How do I do that to create sort of new types of structural systems?
Mm,
And then the biggest one is our high rise version of cold form steel, right? So that's leading to what was CFS-NHERI work and what we call CFS-10,
cool.
where we'll talk more about that. But
Yeah, we'll get to that in a
that's
minute
super
here.
exciting.
Yeah, I'm really excited to talk about that. But first, like, are there any misconceptions out there about cold form steel or CFS buildings? Like anything that, if there's somebody from the building industry or researchers or just, general public should know about, CFS and especially your CFS Research Consortium.
Yeah. I mean, I think for most structural engineers that have cut their teeth and spend their time specifying structural steel and reinforced concrete, CFS looks just crazy. It's just too thin. They can't sort of conceptualize that they should be designing, large structures out of that. I might have a different perspective, having spent a career, taking small 2x4 members and seeing them fail at 80,000 pounds, in a rig and things like that, right? So it's different if you've lived it and you see
Yeah.
deformations. This is the big thing with cold form steel. Local buckling is not the end of the game, so you can see visibly see deformations and still have half or three-quarters of the capacity left before you top out the load. That's
Wow.
very different. So when we train structural engineers, we always teach them this word buckling, and we
Yep.
teach buckling equals failure. Buckling is a problem. That's not how automotive, aircraft, space engineers
No.
learn about buckling. That's just this interesting deformation pattern that shows up. Same for
Yeah.
cold form steel. And so that sort of getting over the hurdle of working in a thin structure and dealing with some of the deformations that you see at surface level that don't really correlate to strength is different for structural engineers, and probably the biggest challenge to get people interested and used to using it.
Yeah, well, and not just the engineers, but then the end user as well of like, is that supposed to happen?
Sure, right. Although, as is most of the case with structural engineering, we're behind other
Yeah.
things or whatever. So you don't get to view all the magic.
Yeah, yeah, which sometimes a shame because the magic
It's
is
very cool, right? Yeah, but I
yeah.
mean, we're engineer nerds, so that's a little bit, our definition of cool may not be widely accepted.
Yeah, yeah. As I keep reminding people, like, if you ever think I'm too cool for anything, I've never literally been cool enough for
Exactly.
anything
Yeah,
in
that
my
doesn't
life.
exist.
So yeah, it's because structural engineers, yeah, we're behind the scenes a lot. But some buildings though, you'll have the structure
Oh,
exposed.
actually, the reason I fell in love with earthquake engineering as a student, even though I grew up in the Midwest, was because the structure is so prominent. I mean, like you can tell when you're someplace where earthquakes are important because suddenly the buildings look different, right?
Yeah.
And if you're a structural engineer and you start seeing all that bracing and all these hold downs and like different elements that you never see back at home, you're like, oh, what are these guys? What are they doing
Hmm.
or whatever? And like, the engineer that did this, they must have really, be working on something. And so it's a visceral to me, reaction. I also think that's why you find, in earthquake country and in cultures that have a lot of earthquakes, a different sort of relationship with structural engineers, right? It's a tighter connection.
Yeah, yeah. I grew up in the Midwest too, and we moved out to Oregon a couple years ago. And like, I was walking around the University of Oregon's night campus yesterday, and yeah, the structure is just completely different. A lot more open. You see the bracing.
It's exciting, right? You're like,
It's
yeah,
really exciting. Um, Rather than all right, it's a bunch of bricks all in a box.
yes. Yeah, I'm here at Johns Hopkins University, and every building is, whether or not, no matter what the structural system is, it looks like a brick building. Brick for real or brick facade, one way or another. That's what it's going
Yep,
to look like.
which are beautiful in their own way,
I
but
love it. It's
that's
great. But
alluring.
yeah, yeah.
All right, now we get to talk about I think the what the moment you've all been waiting for, right? CFS-NHERI, where you're at these at UC San Diego, the LH Post shake table. They, as a mechanical engineer, I love what goes on below the shake table, all the hydraulics and everything. But let's talk about what's going on above the shake table getting constructed there. They're really excited.
Well, we should talk about it below the table for just a minute, though, because
Yeah.
this project has been around so long that the LH Post site out at San Diego actually went through an upgrade, right? It was a one-dimensional table, and it is now a 6 degree of freedom table. Um, uh, this particular CFS-NHERI project, which is our cold form, that's our shorthand for our cold form steel project, it started pre-pandemic. And it's, I think, in year 7 now of a
Mm-hmm.
3-year project or something like that. So it's been a long journey. And along that
Yeah.
journey,
The 3-year mission that's now
yes, exactly. We're like the Star Trek guys that got lost.
yeah.
But it's because of the incredible work of Professor Tara Hutchinson, who we'll
Oh yeah.
talk to, I hope, at another time,
Absolutely we
and many of
will.
the other collaborators, but also the industry working hand in hand with NSF to make an enormous project like this happen. So what project is it? We, as a capstone for this effort to really understand the size and performance of taller cold form steel buildings, we have detailed and assembled, and it is now actually on the shake table, a 10-story cold form steel building. The code would limit it to 65 feet. So it is beyond code limits in its height, beyond code limits in its structural system. So we used experimental work from ourselves and other colleagues to develop the actual structural system. So it is really showing us how far we can go with a really lightweight system like this, and really, using that to uncover the resilience and performance of these types of systems. So super excited about just a few months from now, we're censoring now, we'll begin the white noise tests and really start to understand this creature that we've created in out there in San Diego.
No, that's awesome. I'm looking now at if we'll put a link to this in the show notes, but there's live video streams from the shake table on the UCSD's Engelkirk Structural Engineering Center website. and it's there. You know, they got a southeast facing one, northwest and southwest, and it is looking good. It's actually
Yeah.
raining down there.
Yeah, it's raining there. And even the construction was part of the project. So actually, a full half of the building was full 3D modular construction,
Wow.
all cold form steel. So it doesn't have the usual hot rolled steel perimeter frame. So that was a collaboration and additional funding to actually. We designed a sort of stick built, and then we redesigned it for panelized and
Uh-huh.
modular. So every aspect of the building has really been a learning curve for the research team, but for industry as well. We're really
Yeah.
utilizing it to make sure everybody is maximizing what we're learning from that effort.
Actually, what we can do, since this is going to be on YouTube as well, so those of you who are listening on Spotify or Apple Podcasts or whatever, go over to YouTube because I'm going to just share my screen here with the actual
There
thing.
it is.
Talk about.
Yeah. Yeah. So that, yep, it's just topped out a couple of weeks ago, 10 stories tall. You can see it's a kind of effectively, it looks like kind of two rooms, and you can kind of see what would appear to be sort of a balcony. It's originally designed as a large full-scale hotel/apartment building. This is a slice of that building. Then it's a 10-story slice of what would have been a full footprint building. And so those balconies that you can see in the video are actually where it cuts through the slice of those rooms. Had to do some redesign so it could it could stand on its own as
Yeah.
a 10-story building. And you can kind of see where the modules are. So it's panelized on one side, modular on the other. Obviously, this is a building in which we're testing it with full finish systems. So there's the structural
Yeah.
system, the finish systems. There's non-structural in it as well. There's gas lines. They don't have natural gas
Really?
in them, but yep. And sprinkler systems. That's a huge
Whoa.
collaboration that NIST came along and partnered with us on all these non-structural aspects. So it takes a village. You can see banner on the side. You can't see the details of it, but it just goes on and on and on in terms of the logos. This is one of
Yeah,
those
I think there's two
NASCAR
of
sort of
them.
things, like 100
You
logos.
actually topped out one of the vendors.
Everybody that's touched steel is part of this building at
That's
this
awesome.
point. Yeah, yeah, it's
It
fantastic.
and this is like Tara also worked on the Tallwood project with Xing Pei, and you know she worked on the non-structural systems there as well, and so it's really cool to see this take a lot of the lessons learned from that 10-story building and put it into a completely different construction method.
Completely. Working with Tara Hutchinson at San Diego on this is it's just a complete game changer in terms of our pace of work and the depth of what we're able to accomplish. And she is also an incredible colleague and networker in terms of bringing in these partners to make this happen. It's a dream come true to be able to build this. When I tested a two-story building, which now looks so small, on the
Right,
shake
that's just
tables at Buffalo
down
at
there.
Nice. Yeah, exactly. I thought that might be the biggest test I ever do in my career. This surely will be the biggest test I ever do in my career, but I don't know, maybe not, right?
Maybe not, right?
Yeah,
I mean,
exactly, right. So
they're only limited by the FAA out there at
that's
UCSD.
right.
Who
But
knows?
wouldn't be possible without Tara. It's amazing.
Yeah,
And
this doesn't even close to top out the load capacity of the shake table there either.
right, but that's primarily because we're lightweight, right? So
Right.
a 10-story cold form steel building weighs significantly less than tall wood, weighs significantly less than a 10-story RC or structural steel system. So the payload of the table can take more because mass is really what drives what you can do.
Yeah. Yeah. So if you're, out there listening and drooling over this, put in a proposal for a 20-story version.
Yeah, I mean the Miramar Air Force Base is right there, so there will be a limit at some point where they're going to get cranky, I would assume. But so far, so good.
Yeah, I mean, you can. We were out there for the Tallwood test with NSF and our program officer Joy Pauschke, who's been amazing. But their communications guy and I were up on the top floor videoing F-35s taking off and landing and playing the Top Gun theme in the background.
Yep, absolutely. I hope to see you enjoy on the top of this building here in a few months.
Yeah, yeah, that'll be great. But I don't know what the actual ceiling is, but it's a couple thousand feet or something that you could go up to, which would be really interesting. I don't
Sure.
think it's structurally possible.
Yeah.
Yeah. So what are some of the like exciting either structural or non-structural things that you've talked about the modular versus panelized construction. What are some other elements of this that you're really excited to see in the testing to come the next few months?
Yeah, so absolutely. So one of the things that happens as you go up taller in cold form steel and the gravity loads start to get bigger or whatever is you start to get into bigger member sizes. So particularly for the cold form steel shear walls that make up the laterals, the primary lateral system up the heart of this building, and the lower floors, they actually use HSS shapes and power actuated fastener steel sheet. To provide the lateral system. So it becomes a mixture in the lower floors of some hot rolled structural tubes and cold form steel. So that's a great
Oh,
partnership. You're sort of getting into these kind of hybrid type of structures down in the lower floors. Really interested to see how that performs. As we were developing these systems, we came to learn that the West Coast structural engineers had a very different detailing system for the way forces transfer across the floors vertically, like to use a secondary kind of tie rod system. And the East Coast structural engineers, even in the seismic areas, like to use a kind of direct welded type of connection. So we actually have in the north-south and east-west directions two slightly different details for the multi-story system. And we have the ability to test shaking only in north-south and shaking only in east-west because it came at 6 degree of freedom table. So we can do
right.
white noise and really like look at some of these details. So before we replay the full earthquake motions in their full three-dimensional glory, we can actually do some really specific things to understand how some of these details are affecting things. Interior to one of the rooms is a modular staircase, which goes all the way up top to bottom from CS in Texas. Donated the whole system. It's
Wow.
both functionally how we get up and down in the building.
Yeah.
It's also a part of the experiment.
Is it
So
similar to the system from Tallwood
it
or
is, yeah. It's the same company, CS
okay.
Construction Specialties, that provided that. So they're an incredible partner for NSF and in these situations. And we're again looking at different types of detailing that they use to make those systems be able to drift without throwing a lot of stiffness into the system. They're going to be really interesting this time because our system is pretty flexible. So we'll really test out whether they're sort of drift ready systems, exactly how they perform when we're shaking. We're going to do fire tests on this building, so it has
Oh,
full
wow.
shaft well. So when we're done testing, they're going to do fire tests. That's with some additional collaborators, including one of my colleagues here at Hopkins, Tomas Grenay, and other friends. Um, and then I mentioned the collaboration with NIST, which has a number of non-structural systems, which we'll be able to take a look at. So yeah, as a structural engineer, I'm really interested in the overall performance and the load sharing between the designated structural system and all the rest of the building. That's really been the secret sauce of the system behavior for cold form steel, is really understanding that load sharing. And then we've got all these other objectives layered on as well. So yeah, it's going to be fascinating. And right now we're just working on the hundreds and hundreds and hundreds of sensor channels to
Oh
figure out
gosh,
exactly
yes.
what we can measure and what we can't, right? So it's that's the thick of the battle right now today.
Yeah. I was trying to find a picture. I think I found one of the underside of those stairs from Tallwood. See if this will work. Screen sharing is paused. Resume. Maybe.
Yeah, I can certainly share some pictures from our building as well, but it's the same system with that drift ready system that
Yeah.
allows
Well,
that
it's
mid-height stair to kind of float, is the idea.
there we go. Yeah. So this is from the underside of the Tallwood stairs. Um, but yeah, it was interesting to see how this whole system can float around, but it just works like normal stairs.
Yeah. And this comes from observations that have happened post-earthquake where damage in staircases is both the greatest damage that we'll often see even at a low magnitude earthquake and the most concerning because it's egress, right?
Yeah.
So you're like, so the stiffness differential between a conventionally detailed stair and a building can be an earthquake problem.
Yes.
And so there are technologies like this, changes in the codes, changes in the way engineers think about these things. Stairs used to just be whatever, design the building, there's a hole, they're going to put stairs in it.
Yeah. Put
And
stairs
now
in.
there's
Yeah.
and a lot of that work has come from NHERI to really shed a light on our understanding of this. So, it seems like a small thing, the stairs in a building or whatever, but I think the amount of research that's happened to create more resilient buildings because of these particular programs you can really see it in a simple detail like stairs.
Yeah, and it gets to the point of you know, we're both from the Midwest, right? So you got the New Madrid fault that is going to go someday, and is not, you know, something that a lot of structural engineers have thought about until, you know, the past couple of decades. But this is a really poignant piece here to look at, of, you know, as new construction or retrofits are coming in, you know, places like St. Louis, Chicago, Lafayette, where I came from, is, hey, incorporating seismically resilient stairs is a key design consideration in these areas. And it doesn't have to be, I mean, this, at least to me, doesn't look like it would be magnitudes more expensive to install in new construction.
Yeah. And I think we should take pride in the fact that we live in a country where scientific lessons learned like that get turned into building codes, which get adopted by states, which increase the resilience of our infrastructure, of our buildings. And for a lot of my earthquake friends who go every time there's an earthquake in the world, and they go and do surveys, 9 times out of 10, they're seeing the exact same thing that we already understand and have seen before, but that particular country has lax enforcement of its own building rules or hasn't adopted global rules that we know. And so it takes a lot for us to have a safe infrastructure, a lot of science involved, a lot of policy, a lot of people, you know, building code officials and inspectors. But when we do it right, we all benefit from it amazingly. And so, you know, I'm proud to have been part of that in the NHERI and NHERI train over the last, you know, couple decades.
Yeah, exactly. And you know, we won't go into it too much. We don't want to speculate about things, but you know, NARI's coming up on its you know, whatever is next to the next 10 years, and we're just really, you know, all of us are grateful for Joy Pauschke and her support from her, for a program officer point of view at the NSF, and all the other NSF partners that we've had along the way, and looking forward to, you know, even more transformative research. You know, should NARI can continue in some way, shape, or form with
Yep.
all the stuff going on. But
Couldn't agree more.
as you point out, it's in every building that we interact with, either out here on the West Coast, in the Midwest. There's hazards everywhere that, you know, structural engineers need to design for, and it's really cool to see all these innovative methods that not only mitigate the hazards, but are better performing in day to day and also cost perspective as well.
Absolutely. And it's, you know, it's a little bit unique, right? All of this wisdom doesn't get turned into a product that gets sold, and then everyone says, oh, here's this company that made $1 billion that provides this particular safety for you or whatever. They aren't cars, right? I mean, these are public goods for the most part. And so most of these advances are non-proprietary, and then they're turned into wisdom, and in some cases, you know, prescriptive rules that get passed on to the entire body of practicing engineers and architects that create our buildings for us or whatever. So it's a different process, this path of innovation to safety, than the one that most people think about these days with the path of sort of innovation to commercialization. But it's super important, and our society is really relying on it. And
Yeah.
I'm thrilled to get to celebrate it and to participate in it.
Yeah, it's really amazing to see how this is going, and even how, like, how the NSF approaches getting things to market. You know, we've got the new Tips and Science director, or Tips Directorate, that is looking at how we transform research into practice through commercialization, but doing it in an open way. It's really exciting to see where things are going.
Absolutely.
Where can people follow along with your research as we go, and you know, keep on the train with CFS, NHERI, and all the things that you're up to?
You bet, right? I mean, so you know, go to the World Wide Web instead of ChatGPT and get the latest information. CFS10.ucsd.edu has everything about the latest testing. That's definitely where I would send people. CFS-EI is the Cold Form Steel Engineering Institute, cfsei.org. I'm a past president of that organization and a big fan, and they're a great disseminator of everything a person needs to know on cold form steel. And there are many more, but those are two. If you want to do research, or you want to sort of get anywhere on the ground floor of understanding cold form steel, that'd be number one and number two for me.
Great. Yeah, yeah. Keep an eye out on the show notes for those links. And we'll also be getting Tara on here at some point
Awesome.
as well. And when and if there's a public media day or any
It'll
tool
happen. Yep.
like
Nope. It's
that,
coming. Yep. Yep.
yeah, we'll get that there, and I'll see you down there. It's a short flight for me from Oregon, and it'd be nice to escape the rain. Although it's raining there too today, so who
Not
knows?
typically though. I think
Not
they had like
typically.
9 months of no rain. So I mean, on average, you're going to be safe for no rain there, but it does happen from time to time.
Yeah. Well, Ben, it's been a great chatting with you. Looking forward to seeing you in person in a couple months or so, and keep up the great work.
Yep. Thanks so much.
Take care.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NHERI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NHERI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.